is activated for a few millionths of a second, bombarding a target and creating a burst or pulse of neutrons. Since neutrons can easily pass through the tool, the tubing, and the casing, a cloud of neutrons is created within the formation. Initially, at high energy levels, the fast neutrons collide with the surrounding atoms, quickly reaching a lower level of energy comparable to the surrounding matter. This energy level is a function of the system's absolute temperature, and such neutrons are therefore called thermal neutrons. Hydrogen atoms, having only a proton for a nucleus, are of equal mass with the neutrons, and thus are more effective at slowing down the neutrons than a heavier atom of, say, oxygen or silicon. Of course, there are plenty of hydrogen atoms present in two common reservoir constituents, water and hydrocarbons. Once thermalized, the neutrons are easily captured by nearby nuclei, which then release a gamma ray. Of the elements prevalent in the reservoir, chlorine atoms are particularly good at capturing thermal neutrons. The measure of an element's neutron capturing ability is termed its capture cross-section, or sigma. Chlorine's sigma is 570 capture units to hydrogen's 200. Because the capture unit is based on a per gram of atoms basis, chlorine is actually 100 times more effective than hydrogen at capturing neutrons. This is significant because by monitoring the number of gamma rays emitted by the formation following a neutron pulse, we can measure the rate with which the neutrons are captured. This can give us an indirect indication of the relative amounts of high and low sigma elements in the formation. Since formation waters are often quite saline, having large amounts of chloride ions in solution, a rapid decline in the gamma ray count can mean a large proportion of chlorine and can imply a high water saturation. Unfortunately, oil and fresh water have almost identical capture cross-sections. So the use of a pulsed neutron log is restricted to formations having salinities above a certain minimum. Natural gas, on the other hand, has a capture cross-section only about half that of oil. So with the right salinity-hydrocarbon relationship, the tool can distinguish gas, oil, and salt water. On the semi-log plot, we see an initially high count rate due to the large number of neutrons in or near the casing, especially if the casing is full of salt water. After a short time, a straight line decline in the count rate is evident. At later times, still only microseconds, the background gamma ray count rate is essentially constant. The straight line decline in gamma ray count rate is defined by the equation n equals n sub O times e to the negative t divided by tau, where the number of gamma rays observed at time t is equal to the number observed at the beginning of the decline times the constant e to the negative power of time divided by tau. This constant tau is measured in microseconds and is inversely related to the capture cross-section of the formation, where tau equals 4,550 divided by sigma. So determining the slope of the gamma ray capture rate decline curve, we determine the formation sigma. If we independently know the formation porosity, lithology, and water salinity, we can calculate the relative amounts of oil, gas, and water in the rock.